Here's a couple problems that are very much like problems that you might have in your assignment this weekend. Okay? Alright, so it looks like this time we have two current carrying wires. Looks like they cross each other at about 90 degrees, doesn't it? Is there 90 degrees on yours?
Yeah.
I think it's like 90 degrees. Okay, so where are we supposed to find the effect of the magnetic field created by those wires this time?
2 meters away from X.
At X.
And X is 2 meters like this way?
And 3 meters.
Like 2 there, and then how far from this one?
3.
And they could really ask us any spot, right? Like, I mean, it's totally out within the realm of reason for them to ask us about any spot in the magnetic field. So we're going to have to like add 2 of them up on this, aren't we? So we've got 2 fields being produced. So we can use the right-hand rule, but first let's just get the magnitudes of those fields, shall we? So how would I do the magnitude of the first field? Let me make sure this is on.
Constant.
So should we call it, since that was current 1, should we call it field 1? And it's 4 pi times 10 to the negative 7th. Isn't that mu sub naught? Mu naught? And then times the current. So for this wire, I'm going to have 5 amps for my current. And I'm supposed to go what on the bottom?
2 pi.
It's like a circumference of some kind. Why do you think it's a circumference of some kind, guys? Because it's like a circle, right? And that's kind of like the length that it's being directed over. I mean, we could go through that derivation too, but it should make sense that it's kind of like the circumference of the circle of the field. Anyway, so we've got like 2 pi, and this was 3?
Yeah.
Okay, sorry. Okay, what is that? And I'm going to use another color and do the other one. Oh, my green is dying. Use something else.
3.33.
So this one's going to be 4 pi times 10 to the negative 7th. It's got 7 amps in it, and we're looking at 2 meters away from that.
There we go.
3 point
3 for the first one.
Please.
10 to the negative 7th? Is that right?
The second one is 7.
The second one is 7. Oh, sorry.
Tesla's 7?
Yeah, this
I think I remember that. That's right.
0.
Negative 7 still right? Okay, so now we've got to think about how those interact with each other. Now remember, when you have like 2 vectors, these are vectors, aren't they? These are not scalars. They're vectors. As you could see on that previous thing in the handout, they're vectors. The vectors could either completely add, they could completely subtract from each other, like try to cancel each other out, or if there's an angle in there, you'd have to do what we've always done with vectors and like do what formula? So if there was some kind of angle, we'd have to go, the resulting force vector would be, or there was, in this case, are we doing forces? We're just doing the field, right? So the resulting field vector in this case, if there was an angle, I'm not saying there is, but if there was, it would be, how would we come up with that?
Square root of b1 squared plus b2 squared.
Now I don't think we're going to have to do that on this case, because don't they have like the exact like opposite or the same direction? What is it? Let's use our right hand rule and think about that. Okay, so if we're thinking about this wire, it's flowing up that way, so I put my thumb up that way and I try to rotate it, and over here I can see that it's going in, right? So in blue, let's say we have going in right there. And then I did the other one in red. So if I think about that and I try to rotate my hand down here, you can see that my finger is pointing out. So I think they're completely what to each other?
Parallel.
Anti-parallel, thank you. They're completely anti-parallel, so instead of adding, they're going to like try to cancel each other out this time, right? So which one is bigger? Which one is the bigger field?
I know what it is.
B2.
I know what it is.
B2 is the bigger field, so the net effect is this field Is the field coming out of the page, out of the board at us, or going in on this one? It's coming out. How much?
Seven minus
7 minus that. Does that make sense? So the net effect is this one's going to be coming out since that's stronger, and it's going to be canceled by 3.3, so 7 minus. We good? So we're going to say B net right here is equal to, what is 7 minus that? 4.7 about? 3.7? You didn't see that? Out. We could write the word out. Okay? So we don't have to worry about any angles on that one. I'm guessing on this problem we might have to worry about some angles. And I gave you a couple tough problems this time, so you're definitely going to have to be very careful with your vectors. All right, so let's look at this one. It's the last one for today, probably.
Number 5.
Oh.
Yeah, I'm going to number 5. Number 4 is a good exercise for you guys. I think that one shouldn't be too hard at all. Okay. Number 5, it says find the magnitude of the B field and sketch it at this spot and at this spot. One of those two questions is much easier than the other one. Which one's easier? X or Z? Well, why would it be X?
Because they're opposing each other, right?
How much are the amps on these? Did they tell us?
2 and 6.
So this one's 2 amps, and this one is 6 amps. Okay, so I think that a line directly between them is going to be the easiest to do. So this one we'd be going out, right? So which way is it pointing? It's like up. This one's going in. So which way is it pointing if we rotate back? Up. So are they going to add or subtract?
Add.
They're going to add, right? They're both going up. So I might draw that right away for the direction. Can we do that? So right here, let's draw the direction. I'm going to go in blue. So I'm going to say like there is like B1, and they're kind of going to add to each other. I like to draw it like that. You can see that they're adding, right? It's my own notation. Okay, so let's do that one first. You guys, why don't you figure that out? That should just take you a second. That's easy. How much is that?
Numbers.
See, and sometimes I like to leave the mu naught in there until the end, so I don't have to like keep doing it. So then I can like combine like terms. Oh, those aren't quite nice. I don't know. Do we have it yet?
6 times 2, 7.
Make sure you get your direction on there up. What's a way we could use vector notation to make this helpful for us? I wanted to make sure I give you some multiple options. You could just keep track of it like that. What vector value, which unit vector was it in physics that was like, this is the y direction, isn't it? So we had like the y unit vector, we had like the x unit vector, and we had like a z unit vector that you guys probably haven't used very much yet, but might be helpful in these problems. I, j, and k. I is x, j is y, and k is z. Since this is the y direction, both of these are directed in the j. You guys remember this notation? I do kind of like it for these magnetism problems. So instead of saying up here, I could put just j. If you wanted it to be like down, instead of saying j, you'd say negative j, right? And then it kind of helps you keep track instead of just the visual. I kind of like that notation. It's up to you though, I don't care if you use it or not. And the physics test won't care if you use it or not either. As long as you say how somehow which way it's going. Okay? Let's answer the last question for today and do Z. And I know that I gave you, I think, 2 problems that had this kind of thing in it.
Maybe subtracting to add.
What, on this one? They're both going the same direction, right? So they should be like just summed up.
Oh,
I mean, they could both be going the same direction down too, and then instead of saying J here, we'd say negative J. It'd be the same magnitude, right? Good questions. Okay, so now let's do Z. All right, so let's try to use the right-hand rule and think about the direction here first, shall we? So I'm going to do the Z in red. Okay, so same thing. Let's go into the board and think about what it looks like over at Z. It's a little tough with the right-hand rule. What can you do to help yourself if you really need to? Draw a... This is what the field actually looks like at a distance of Z, right? Make Z the radius of a circle from there to there. That's the center of the circle. Make this a radius and you'll see that what happens? It's going like that. And this one, if you put your hand on there and you like curl it back around to the location of Z, or you draw a big circle like this, which direction is it going to be right here? It's going to be that direction. Which one of these is technically going to be a stronger field, you guys? The one from the 2 amp wire or the one from the 6 amp wire? 6 amp, so this vector should probably be shorter. It should be shorter, shouldn't it? Because it's coming from that guy. If we want to have like a kind of a nice drawing. Okay, I'm going to erase this part. Anyway, there's another thing you can do besides the right-hand rule, though, is just kind of draw a circle, because that's the way that this field is. It's circular around the wire. Okay, so the problem here is, do they perfectly add or perfectly subtract? No, and that's what makes this a little bit tougher mathematically, so we've got to figure out how we can do this. So we have to split it into vector components. Okay, so how can we do that?
Sine of stuff.
Sine and cosine of stuff.
Yeah.
We kind of need like an angle to go off of though, right? So I'm going to do this. I'm going to introduce a horizontal so that we have like a nice reference we can build our angle off of. So this angle right here is the angle for that little vector, isn't it? That's what we need. And then we can do cosine of sine of it. This angle over here is what we need for this vectors. So how can we come up with this angle? Let's just focus on that.
No, that's right.
How can I get this?
You probably have to solve the angles for that triangle.
Ah.
Yeah.
What angle in the triangle is the same as this?
The
other one.
The one
This
by
one?
No, other one.
The
This
other
one?
No.
Definitely not, right? That's a right angle, that's an acute angle.
The
It's
other
this one.
Yeah.
Other
This one and this one are the same. Let's call this theta 1. Why are they the same? Alternate interior, right?
Laws and stuff.
Okay, and this one's the same as
The other one.
this one by
But
alternate interior. So let's call that that. As soon as you realize that, I think this problem's not hard anymore. That was the tricky part of this problem for me at least, was making sure that I could focus on which angle do I actually need. I need the angle from horizontal so that I can calculate the x and y components of both of these vectors. If you guys think of that, I think you'll be able to do the little bit of geometry and stuff. It's just making sure that you know what angles you need to figure out those components, okay?
6.8.
All right, so now that we figured this out, I think that this isn't going to be a big deal. My God, guys. Okay.
We found the angle. We're doing good stuff.
Oh, I believe it.
What you guys get? 36.86 something, 87.
Okay, so they computed the angles. How'd you compute the angles, guys?
Inverse tangent.
Yeah.
Of theta 1?
Yeah.
Yeah.
I'm going to go up here. This is theta 1, right?
Yeah.
So you go inverse tangent of
3/4.
3 over 4, or you could use an inverse sine or cosine, I think, right? So they went for an inverse tangent of theta 1. Looking at this version, it's 3 over 4. So theta 1 was like 30 some degrees.
36.87.
Okay. And then same thing over here. If I look at it from right there, the inverse tangent of 4 over 3.
Or you could just say 90 minus.
Oh, you could. So that's true. I'm just going to do the same thing though. So what is theta 2? 90 minus, it's going to be like 60 something or 50 something, isn't it? 50. Okay. So we've got our angles. Like I said, as soon as you can realize that this is the angle you need, you're going to be good. The rest of this isn't bad, right? We just add up x and y components. So, all right. So B1 is this guy, right? That's B1. So what is this guy going to be? You know what? Let's just do, instead of doing B1 and B2, let's just do B net x and B net y. Wouldn't that be smarter? So the x components. Is this guy's x component, that part, going right or left? Looks like it's going right. Is this guy going to add or subtract from it x component wise? It's going to subtract from it, right? So for x components, when we want the adjacent part, what do we use? Sine or cosine? Cosine. So we're going to go, that guy's magnitude, did we have it? We had it from before, didn't we? What was the magnitude produced by this wire?
1.3 times 10 to the 6.
I'm just going to write it down. Times 2 over 2 pi. How far out is it? 3. And then we said we're going to multiply by the cosine of 36. I'm just going to go 36. Okay? And then we said, okay, for the net x direction, we also need this part. So that's going to be minus, right? So we're going to go minus, oh my gosh. I'm just going to say mu naught. This guy is 6 amps, 2 pi, this is how far? And times the cosine of what? 53. We'll see what that is. Okay? All right, then this guy down here, we're going to go mu naught times y components. They're both going up, aren't they? So they're going to add to each other. So I'm going to have mu naught times 2 pi over 3. So this guy is the 36 degrees, so sine of 36. Then we said they're going to add, right? So we're going to have mu naught times 6 over 2 pi. That one was 4-way, times the sine of this angle was 53. Get that number. And of course, we'll need a calculator assistance on this one.
I could do that in my head, yeah.
Yeah, that'd be impressive.
I wouldn't be impressed with myself. I'd be like, what?
You can't do that in your head, please. Can I leave you in there though?
No, you've got to incorporate the 4 buttons.
Dang it.
All day. Get reduced from 5. It's the cosine of 36 that's going to throw me.
If you're in degree mode, right? This is the scourge of the 83, Paul. Oh, you have one too. Oh no.
That's why I'm not doing it. I'll wait for them.
So many parentheses.
Yep.
See, that's why I bought an 89 when I was in college. It was for this reason right here. $200. I was like, is it worth it? Yes. Yes, it's worth it.
So like,
Alright, but B net
It's
Y.
like, what, 1, 2, 3 parentheses, and then you can start.
And then you can't tell if you made a mistake. You can't like look at it, right? So
Down.
you know how to use the alpha y equals thing though on other people's, Jessica?
I don't think it has a problem.
It doesn't have one, but I'm just saying that way when you take the AP exam, I can let you use mine. If you practice with Todd a little bit or Adam or something. And I don't have this issue.
Let's see what it does.
I should make sure it's perfect. No, it improves your life.
By a lot.
Wrong.
I think Adam showed that to me and I was like, whoa, it really does this now?
No, yours is supposed to be this way.
$200 down the
Mine's
system.
being able to be.
They didn't do it until like the last 4 years though, it wouldn't have helped me.
What are the answers? I have the first one.
I got the x one was negative 7.268 times 10 to the negative 8.
I concur.
Yeah?
Negative 7.268 times 10 to the negative 8.
For the X one?
Good afternoon, Ryan.
Uh-oh.
What do you
The
get?
girls have a basketball game tomorrow and
7.66 times 10 to the negative
boys
8.
basketball
I also
plays
used
tomorrow at 4:30.
36.40.
Oh, that would change a little bit.
That changed.
All the students,
7.8.
It's probably
ACT
really small
boot camp,
now.
last day today to sign up,
10 to the
$25 fee is due to Mr. Janetta. And track athletes, practice starts Monday, all paperwork, fees, and your physical are due
Yeah.
before you can
Use
practice.
the
Thank
exact
you.
numbers.
What is it, Alexa?
7.3 times 10 to the negative 8.
In the negative.
Negative.
So.
Yeah,
just be like
so
left.
that's a direction though, so.
So it'd be like,
That's it?
I mean, it's negative, but it doesn't,
Okay, whatever.
it
Yeah, that's
doesn't
fine.
really matter.
Okay, this one?
I got 3.2 times 10 to the negative 7.
Did you change your sign from plus to minus, adding to subtracting?
What do you mean?
You guys have
Because
3.2?
I did-
I have different numbers here, but I don't have all my work, so I can't
Because
see what
if
I did.
you
I got
subtracted it, because the sign on the
2.13.
top changes.
2.13
from
times 10 to the negative
Well,
7?
I added.
Hmm.
I got 1.2 times 10 to the negative 7.
I may have to.
Did we all get different answers?
I'm getting 3.18 or something.
Yeah, I got
3.2.
3.2.
Yeah, times 10 to the negative 7.
Yeah.
That's what I got, so.
Or,
That's what I got.
use calculators.
or this.
I knew it was exactly.
When the bell rings, I need the following students to report to Mr. Hale's room. Aspen Jones, Laura
Yeah, I
Ambler,
got 3.
Sarah
I missed a 6.
Collins, Sarah Lesser, Tanner Houghton, Alyssa Wise, Logan Newmeister, and Sam Quintana. When the bell rings, I need those students to report to Mr. Hale's room. Thank you.
Jason.
3.18.
You should really use alpha y.
For the 7, 10 to the negative 7.
So 3.2. Hold on. So how would we get the resulting vector magnitude?
Square root of stuff added squared. Greatest explanation ever.
Okay, and how would we get its direction?
We already tangent.
We would look right here. So I'd look at these, draw a little parallelogram. You guys remember our parallelogram? And
Could I have all the boys
draw that guy
basketball players
and then
to
do the
gym
arctangent
for
to
about
actually
2
see
minutes?
what
All
it
the
is.
boys basketball
Okay.
players to the gym for about 2 minutes.
So